Voltage drop occurs when electrical resistance reduces the voltage over a long distance. The National Electrical Code recommends limiting voltage drop to 3% for feeders and 3% for branch circuits, with a total voltage drop between both the feeder and branch circuits limited to 5% combined. This is referenced in Article 210.19, informational note, and then again in 215A2, informational note number 2. So mentioned in there twice, basically both say the same thing. Feeders 3%, branch circuits 3%, with a combined total voltage drop no more than 5% on the whole circuit. So there are 5 key variables whenever you do a voltage drop calculation. I have the formula written up here. This is for 3-phase systems, but the 5 key variables that we need to figure out before we can even get started are: number 1, the wire type. Do you have copper or do you have aluminum? Both vary in resistance. 2 is if you have a single phase circuit or a 3-phase circuit. 3-phase is a little bit more efficient than single phase, so you're going to have a little bit more of a favorable number there. Part 3 is the wire size. An American wire gauge or AUG, AWG. Larger conductors are going to have less resistance, right? Part 4, the 4th variable we need is the load in amperage. So you're trying to determine what the demand is going to be on that wire. A higher demand is going to increase resistance on it because it's going to increase the heat. There's some other variables involved with that, but the load does play a factor in determining your voltage drop. And then the last variable we need is obviously wire length. Wire length, the further you are, the more resistance you're going to encounter. To really get started, we need to look at one table in the NEC, which is going to be in Chapter 9, Table 8, Conductor Properties.
Here we are in Chapter 9, Table number 8, Conductor Properties. This table provides a lot of information about the conductors we use in the field. It provides the area, conductor properties such as the number of strandings, the diameter of the strandings, and then the overall dimensions, including the diameter and the area of the conductors. So a lot of this information is kind of used in different areas, not for figuring out the voltage drop calculation. So we're not really going to look at this section here in the center. The last section is going to be the DC resistance, and then you have copper and aluminum. Copper has 2 sections of uncoated and coated, and aluminum is just by itself. So I know what you're probably thinking. This says DC resistance. We can use direct current resistance on alternating current conductors up to 1 aught. 2 aught and above, you'll need to include the alternating current adjustment factor, which can be calculated using the values in Chapter 9, Table 9. We can jump to that in another video, or you can research skin effect for a better understanding of why. Let me know in the comments if you're interested in another video covering that. The resistance for conductors of 1 aught and smaller is basically the difference in resistance from DC resistance to alternating current resistance is considered negligible, and so that's why it's not included. This is a general rule of thumb and not something set in stone. So again, whenever we're looking at table number 8, here you'll find your wire size, say for example number 8, and you would just follow it straight across, and you can find your circular mills right here, which circular mills is what we're going to need for calculating our voltage drop using the formula. Here in stranding, it's saying quantity 1 and quantity 7. This is not saying you have 7 wires. This is saying that this is solid and this is stranded. And there are 7 strands in a stranded number 8. So this quantity, don't get thrown off by that. We're still talking about 1 wire. That's why the circular mills doesn't change. There is a slight difference in resistance, but we'll cover that whenever we use Ohm's law to cover voltage drop. But for this video, we're going to really focus on just using the voltage drop formulas. Up here, you can see uncoded and coded. We primarily use uncoded out in the field. Coded is going to be a wire that has tinning or some other treatment done to the copper that would affect resistance. It's not a huge difference, but that is something to be aware of. And then here we have ohms per kilometer and ohms per kilofeet are 1,000 feet. Here in the United States, this is what we'll use, the ohms per kilofeet. So again, looking at our example here of this number 8 wire, we see it has a circular mill of 16,510, and if we were using our uncoded ohms per kilofeet, it's 0.764. Those are the two numbers we're concerned about when we're doing our calculations for this. Another kind of side note on this, there is that K factor. We haven't really discussed K factor yet. So K factor is built into all of these numbers. A great example would be 1000 kc mil going across. You'll see our ohm per kilofeet and our ohm per kilofeet for aluminum, right? We'll look at these two columns here. So our ohms per kilofeet is 0.0129 and 0.0212. To figure out the ohms per feet, you take this number and divide it by 1,000, right? Because it's per 1,000 feet. And then you multiply your ohms by the circular mills. So since this is 1,000 kc mil, we would take 0.0129 divided by 1,000, and then we would times it by 1,000 times it by 1,000, because again, this is kc mil. This is 1,000 circular mils, so you have to times it by the kc mil, and then times it by the circular mil, and then times it by the kc mil. So it's 1,000 times 1,000. 1,000 is the circular mil, and then we would times it by 1,000 again because it's 1,000,000, or 1 million to put it shortly. And if you did that, you would get 12.9, which is the K constant or K factor for copper. And if you did the same for aluminum, you would do 0.0212 divided by 1,000 times 1,000 kc mil times 1,000 cm, and then times another 1,000 because it is kcm. So that would also give you the number or the K factor that we use in our voltage drop formula of 21.2 for our aluminum. If you do that math for any of these, so if you take, let's just say this one here, if we take our uncoated copper and we take this number and try to figure out ohms per feet, we would take 1.21 divided by 1,000. And if you take that and you multiply it by the circular mills, that'll be 1.21 divided by 1,000, which is 0.00121. And then we'll times that by 10,380. That gives us 12.56 roughly, which is pretty close to the 12.9. They are all roughly going to get you a number pretty close to 12.9. So the K factor is baked into all of these numbers already. That's how we can do the math to find out what the K factor is if we forget it. The easiest one would obviously be for 1,000 kc mil and not just 1,000 mil. So it should be 12.9.
Now that we've taken a closer look at Chapter 9, Table 8, we've kind of already seen the different information that table provides, and we're also able to look at not only the circular mills, but how the K factor or K constant is baked into the chart itself. We can start to look at the two formulas. So again, I have the three-phase formula, and I'll just write it in bigger up here. So voltage drop for a three-phase system is equal to 1.732 times K times I times L divided by our circular mill. And for our single phase systems, it's going to be 2 times K times I times L over Cm. The only difference between single phase and three phase is this is 1.732. It is a little bit more efficient than a single phase circuit. And so that's the one thing you have to remember whenever you're doing your voltage drop calculations. And so I do have it written down up here as well. Voltage drop is going to give you your voltage drop in volts. This whole formula is going to be your end result is going to be in volts. K, again, is that K constant that we saw in Chapter 9, Table 8. It's going to be 12.9 for copper conductors, whether or not you use the chart or not, or the table, excuse me. And then for aluminum, it's 21.2. Those are always the same. Your I is your current in amps. So whatever the load is on your conductor, that's the one you're going to want to put in here. L is for the length of the conductor in feet. And then Cm is the conductor area in circular mills, which we saw. Again, that's the information you get from Chapter 8. So we'll go ahead and work through a couple of examples to get you familiar with how this works. Let's go ahead and take a look at this example that I wrote on the board real quick. We have a 120 volt single phase circuit. It's going to have a 50 amp load using number 8 copper with a wire length of 150 feet. I had to write our formula down here, but if we want to figure out the voltage drop for this, we would do 2 times our K constant is 12.9 for copper, not for aluminum, so remember that, times I is going to be our load in amps, so that's 50, and then we're going to have our length of 150. All of this over the circular mills for number 8 copper. This is where we would reference our Table 8 in the NEC, and it comes up as 16,510 circular mil. So now all we have to do to figure out our voltage drop is pull out a calculator and do this math. 2 times 12.9 times 50 times 150 gives us 193,500 divided by 16,510. This gives us a effective voltage drop of 11.72 volts. In order to convert our voltage drop to a percentage to see if it complies with the rules in the NEC, we would take the percentage of voltage drop is equal to the voltage loss over the voltage supply times 100 to get that as a percentage. So in our case, it would be 11.72 volts over 120. Let's go ahead and do that math. 11.72 divided by 120 times 100 gives us a percentage of 9.77%. So as we can see, this exceeds the 3% for the branch circuit that's allowed. So that means this number 8 conductor is too small, and we'll have to go up in size to make this compliant. We can also use this same question, but instead of doing a single phase, let's go ahead and do a 3-phase branch circuit to see what the result is there. As mentioned before, the really only difference between the single phase and 3-phase calculation is that first number. Instead of being 2, it's going to be the square root of 3, or 1.732, and that is going to be the math we'll use to figure out the voltage drop. So our new voltage drop, let's go ahead and get a calculator out and do our math here. 1.732 times 12.9 times 50 times 150. Again, this is going to change our numbers slightly. So I think we're at like 190,000 last time. We're at 167,571. We'll divide that by 16,510. And instead of being 11 something, we are now at 10.15 volts. If we want to figure out the percentage of voltage drop, it would be voltage loss over voltage supply times 100. It would be 10.15 volts over 120 volt times 100. .15 divided by 120 times 100. .46%. So again, we're still exceeding the 3% threshold, even if this was like the full combined length of the feeder and the branch circuit. We're exceeding that 5%. So this number 8 wire supplying this 50 amp circuit would be too small. So we would have to upsize it to a larger size to accommodate for the voltage drop. For our next example, let's look at a 3-phase feeder that's supplying a 45 amp load 104 feet away. And again, on a 3-phase 120/208 system, we'll use copper number 6 as our feeder wire, and we'll run the calculation. If this sounds familiar, you're probably a student in one of my classes, and this is an example given then in the class. So might look familiar if you've taken one of my classes before. So for this example, we're going to have a 120 208 volt three-phase system with a 45 amp load at 104 feet in distance or length on the conductors, and we're going to be using number 6 copper. So I've already wrote down the formula and have it written up here. Again, for a three-phase system, we use the square root of 3, our 1.732. Our K constant, our K factor is 12.9 for copper. We have a 45 amp load at 104 feet, and we're using number 6. So if we go to chapter 9, table 8, we look at number 6 and we find the circular male area. It's going to give us 26,240. Doing the math out, we get a voltage drop of 3.98 volts. Throwing that into our voltage drop percentage formula over here, voltage loss over voltage supply. Our supply is 120 208, so we're going to divide by 208. It's not an individual branch circuit. We're using the actual feeder. It's going to have a full voltage of 208. And so we'll do that times 100, and it gives us an effective voltage drop of 1.91%, which is well within the 3% allowance given by the NEC. So this is 100% compliant as it stands without any other correction factors. You do want to take into consideration your more than 3 current carrying conductors, and you also want to look at your ambient temperature adjustment factors if those aren't applicable. So this is a good example of how you use both the branch circuit voltage drop calculation. If it's a branch circuit, you do 120. If it's a feeder, you would do the larger voltage. And again, we saw the difference between a single phase and a 3-phase system. Always calculate your voltage drop to ensure compliance with the NEC. Selecting the right conductor prevents excessive energy loss and equipment damage. So hope this video has been helpful for y'all. Again, leave me a comment, subscribe, all that jazz. Thank you.